A warm welcome. This is Control Systems course with lecture 1.3 focusing on electrical analogy of mechanical and thermal systems. Mechanical system, it is of two types, namely mechanical translational system and mechanical rotational system. While considering the mechanical translational system, there are three main components, namely an ideal mass, a friction element, that is a dashpot, and third is a spring element. Normally, differential equations are used to represent these three elements, namely, while it is mass, the force on the mass element is represented as Fm is equal to m into d square x by dt square. Similarly, if it is a dashpot element, then its force is represented as Fb, which is equal to capital B into dx by dt. And if it is a spring, then it is represented as F is equal to Fk, which is equal to k into x. So this d square x by dt square term will represent the acceleration value if x is supposed to be the displacement and dx by dt is supposed to be the velocity. Mechanical translational element, a small example is being represented here in the figure, which is a simple translational mechanical system consisting of a mass, a spring and a dashpot. Here a force is acting on the mass, pulling the mass outwards. So when a mass is pulled outwards, obviously the dashpot and the spring element which are connected to the mass will also be getting displaced. So this displacement is considered as x. And initially we'll be drawing a free body diagram representing all the forces which are acting on the mass, and this force, it will be considered as an algebraic sum of the externally applied forces to any body, which is equal to the algebraic sum of the opposing forces restraining the motion produced by the elements present in the body. So this is given by the D'Alembert's principle. According to this principle, the total forces which are acting on the body will be considered, the summation will be considered to be zero. So here we can see in the free body diagram, it is nothing but F of t, which is an outward force, and we can see the other forces which are acting towards the mass element. So in this case, we can consider the total forces as F of t minus Fm of t minus Fb of t minus Fk of t is equal to 0. In this way, we will be constructing the differential equation. So this is a small example. Here we have considered the mass element. Sorry, this is station, and here we are considering a small example. Here we have M1 and M2, two different masses are being considered, and while considering the mass M1, what and all the elements which are connected to the mass are K1 element, which is a spring element, then the dashpot B element, and finally the K element K2. So while considering the elements B1, which is connected as a dashpot, that is the friction between the plane as well as the mass. So here we have a wheel attached to the mass, considering it as a moving mass, and that will be a friction between this wheel and the plane, and here it is B1. Here we can consider the first mass initially, and then the second mass will be considered. In case of second mass, we can see the dashpot B, the K2 spring and the B2 friction are considered along with the M2 mass element, and also a force F of t is acting in mass element M2. So we can see when F of t is applied, I mean when M2 is pulled out, it will be moving, and this B2 value will also be this element will also be changing, K2 will change, B will change, obviously M1 is also connected to it and that will also be changing, and the element K1 and B1 will also be changing. So when force is applied to one mass, all the interconnected components will be changing. So let us consider two different displacements, namely x1 and x1 in connection with m1 and x with connection with m2. So what is the question asked is we have to determine the transfer function after writing the differential equations. So let's see. This is the free body diagram of the mass element m1, and we can see the varieties of elements which are connected to it, and based upon this we will have this equations, differential equations. Since it is mass element, we'll have acceleration. Since it is a dashpot, we'll have a velocity attached to it, and since it is k, I mean spring constant, we'll have displacement along with it. While considering the dashpot B and spring constant K2, they are connected to both the mass elements. So while writing the differential equation of B and K2, we can have to consider both the displacements, that is x1 and x2. So the difference between the two displacements will be considered. And next, by Newton's law of sum of applied forces is equal to the sum of opposite forces. We consider that law and applying on it, we'll have the equation set up as m1 d square x1 by dt square plus k1 x1 plus b1 into dx1 by dt plus k2 into x1 minus x plus b into d by dt of x1 minus x is equal to 0. This is how we'll frame the differential equation for mass m. Similarly, for mass m2, you have to consider the same pattern of representation, and finally we have this equation f2. So now we have two differential equations in our previous equation. So this x1 of its value, which is represented with respect to x of in this case, and so we'll have this equation in terms of x of s. So already we have one term with x of s, and here the x1 of s is being converted to x of s term, and finally we are reducing the three different variables into two variable. So two variable representation, f of s is nothing but the input and x of s is nothing but the output. So we have the output and the input component for finding out the transfer function. So what we are doing is we are taking x of s outside from all those equations, and we have a representation here. So now obviously transfer function is nothing but x of s by f of s. So while dividing that, we'll find out the transfer function of system. So this is how we have to find out transfer function from the MBK system, that is a mass, dashpot and spring system of mechanical translational system. Instead of k into x, 1 by L into integral of v dt, and in case of m into d square x by dt square, it is c into dv by dt. In this way, we can see that an R, L and C component are connected in parallel. So this is a parallel circuit with the current source. So this is how the force current analogy is being used for representing the electrical system of the mechanical translational system. Similarly, for mechanical rotational system, the main difference is we have the moment of inertia as J. As we consider mass in mechanical translational system, here the moment of inertia J is considered, and here instead of force we will consider the torque obtained, because it is a rotational system. So the rotational displacement will also be considered as theta instead of x. Instead of force, we have torque T. Hence, the balanced equation is nothing but T is equal to, here we have only three elements. It is J, D, and we have a constant K. Actually, it is not represented. We will have a constant K. Let us consider. And in that case, the torque balanced equation is nothing but T is equal to J into d square d theta by dt square plus b into d theta by dt plus k into theta. So we have torque voltage analogy. Instead of force, we have torque here. For torque, it is voltage. For moment of inertia, it is L. And for frictional constant, it is R. For K, it is 1 by C. For angular velocity, omega. Angular velocity is nothing but d theta by dt. For angular velocity, it is omega. For omega, it is current I. So in this way, when we represent, we get a mesh equation here, similar pattern, and the RLC. And the current, while considering the torque current analogy, instead of torque we can have current, instead of moment of inertia it is capacitance C, and others are the same. Instead of V it is 1 by R, K it is 1 by L, and for angular velocity omega it is voltage V. Well, we substitute the pattern, I mean the electrical pattern of the mechanical rotational system, we get a parallel RLC circuit. This is how current analogy system is used for representing the mechanical rotational. While considering the thermal system, there are two fundamental thermal elements, namely thermal resistances and thermal capacitances. So this is how we are considering a system here. Here, this is the temperature